In this video we're going to look at an object falling under the force of gravity. So the idea is you've got a ball, you drop the ball down towards Earth, there's the Earth there, and we know that it accelerates down to Earth, so acceleration equals 9.81 meters per second squared. So we're able to say then that the acceleration is a constant, 9.81 meters per second squared. We'll give the constant a name, we'll call it g. So it's acceleration due to gravity. So we're able to rewrite that and say, well, acceleration is equal to the second differential of position. Okay, so we can then say that's going to be d squared y by dt squared, where y is just this axis here. So we're able to say that there equals gravity. Okay, so that's our little differential equation. D squared y by dt squared equals g. Now we can go to solve that equation by straightforward integration. So if we integrate the left hand side, we're just going to be left with our dy by dt equals, well, it's going to be gt plus a constant. The constant is going to be the initial velocity v0. So you're able to say then that v equals gt plus v0. Okay, so that's equation number 1. Now if we integrate that again, you're going to be able to get the position with respect to time. So you're going to have y is going to equal a half gt squared plus v0 t plus a constant. Now the constant is going to be the initial position, which we'll just call it y0. Okay, so that's the second equation. So we'll get two equations. One gives the velocity in terms of time, one gives the position in terms of time. So if we were to say then that the initial velocity equals 0 and the initial position equals 0, so if we put these into equations 1 and 2, then you're just going to be left with two equations. We're going to have v would equal gt and y equals a half gt squared. Now we can see from these that velocity is directly proportional to time and position is directly proportional to time squared. So if the time was doubled, then the velocity would be doubled. But if the time is doubled, the position would go up by a factor of 4. And if the time is trebled, the velocity would be trebled, but the position would go up by a factor of 9. So that's assuming that we have a constant acceleration due to gravity. So we can see from that then that the kinetic energy would have to be proportional to the velocity squared. So that's just a little aside. Now if we were to look to find out what the velocity is dependent on the position, then we can take these two equations and we can get rid of the t. So we can write this one here as t equals v upon g, and this one here we can write t equals, it's going to be root 2y upon g. So then we can say this equation equals that equation. So we can say that v upon g equals root 2y upon g. So then we can say that v upon g equals, I've already written that one down, haven't we? So v is g root 2y upon g. Okay, so we don't need that there. So then we can say that v equals g root 2y upon g. So then you can say that v equals root 2 gy. Okay, so that's going to give us our position, our velocity, in terms of our position. Okay, so now we'll go on and we'll have a wee look at an idea of terminal velocity. So let's assume that there's a retarding force, so whenever the ball drops down there's an air resistance, a wind resistance, and the wind resistance is directly proportional to the velocity of the ball. Okay, so let's make that assumption and we'll see where we go for there. So we're able then to rewrite the differential equation as d squared y by dt squared equals gravity, but we'll be taking off the retardation, which is directly proportional to the velocity, which is the change in position with respect to time. Okay, so that's our new little differential equation. Okay, so now we want to go ahead and solve that. So again, we'll separate out the variables. So we can write this left hand side as that's going to be dv by dt equals g minus c times v. So we can take this g minus cv down and the dt up, so and then we can integrate. So you're going to have integral of 1 upon g minus cv dv is equal to the integral of dt. So the left hand side can be integrated as minus 1 upon c, it's the log of g minus cv, and the right hand side will just be t plus some constant, we'll call a constant c1. Okay, so taking the minus 1 upon c across, we're going to have our log g minus cv is going to equal minus ct minus c1 times c. Now if we take the exponential of both sides, we're just going to be left with our g minus cv equals, well, that's going to be e raised to the power minus ct minus c1c. So that can then be written as g minus cv equals e to the minus ct times e to the minus c1 times c. Now the c1 times c is just going to be a constant, so we'll take that down and that will give us our g minus cv equals, we'll call it c2, equals c2 e to the minus ct. Okay, now if we say that v equals 0 whenever t equals 0, then we put this in here, so v equals 0, that end will equal 0, so we just have c there, and when t equals 0, that whole thing would tend to 1, so we just have g would equal c2. Okay, so those are our initial conditions, so we can say that our g equals c2. Okay, so we can then rewrite that, almost finished now, we can rewrite that as g minus cv equals, well, the c2 gets replaced by g e to the minus ct, so that's minus cv equals minus g plus ge to the minus ct, so we can say that cv equals g minus g e to the minus ct, so we can rearrange that for v and say v equals g minus ge to the minus ct all upon c. So finally we can then say that v equals g upon c 1 minus e to the minus ct. Okay, now this value here, c, it can be written as a factor k upon m. M is the mass, k is a value which is determined by the shape of the object. So we can say then that the value c is going to be a positive value. So as t tends towards infinity, this whole thing here tends towards 0. So it means that our value v will tend towards g upon c. Okay, so we can say then that the terminal velocity v is going to be given by a factor g upon c, which is going to be g upon k upon m, which is g m upon k. Okay, so our terminal velocity is going to be given by our gravity, our mass, and our factor k, which is determined by the shape of the object. Okay, so that's what the final one that we're looking for. But let's working under the assumption that the retardant force is directly proportional to the velocity, which might not be the case, but it's good enough for us to have a little stab at looking at the terminal velocity. Okay, so thank you for listening and goodbye.